Today we're going to continue by talking about some of the key features of a distribution and how to compare and describe distributions. So the four key features of a distribution that we are going to talk about are shape, center, spread, and unusual values. Let's talk about shape first. So I have 6 pictures on here. I know they're not on your paper, but you can kind of just draw them either in histogram form or dot plot form or even in curve format, because basically what we do with curves is we take the shape of the distribution and we kind of turn it into some sort of curve that makes it look like that as we describe how many observations there have been. So you can even do it in curves. Um, some of these are probably pretty straightforward, and others are a little bit more difficult to remember. So the first one on the top left is going to be roughly symmetric. Now, there are a few more observations to the left than there are to the right, but in general, most of this ends up being something that's kind of in a symmetrical pattern. So that's roughly symmetric. Now, the second one is also symmetric, but we have a more descriptive way to put this. Not only is it symmetric, we would call it uniform. So uniform means that it's pretty much the same all the way across. So that makes sense in results from die rolls. Now, it looks like they rolled a die about 600 times, and they got about 100 for each number. It's not exactly 100 for each number, but it's about 100 for each number. We call that uniform if it's pretty consistent. So the curve would be something that looks pretty consistent all the way across. This third one is also symmetric, but we can be a little bit more specific on this one as well. So or roughly symmetric, approximately symmetric, something like that. So if we're looking at the one on the far left, we would probably call this unimodal and symmetric. But the one on the right is roughly symmetric and bimodal. So the difference is there are 2 high values on the one on the left, or I'm sorry, the one on the right. So there are 2 peaks if we drew a curve, and the one on the left, we only have 1 peak and it's kind of in the middle. So something that's symmetric has symmetry, obviously. Bimodal means we have 2 modes or 2 high points, and then unimodal means we only have 1 high point. Once again, the one on the bottom right is not great in terms of its symmetry, but we would call it roughly symmetric. That's because if we found the mean of this, and we'll talk about the mean later, but if we found the mean, it would be relatively close to the high point of our graph. So the mean is somewhere around here. So that leaves us with these 2 on the bottom left. If we drew a curve, this one has a peak that's definitely far to the left, and then the one in the middle here has a peak that's definitely far to the right. And so if we're looking at these distributions, we call these skewed distributions. So the one that's on the left over here, we call this skewed right. And then the one in the middle we call skewed left. Now that seems a little confusing because the peak is actually opposite of what we talk about. So the peak is on the left here, but we call this skewed right, and vice versa for the other graph. The reason why we talk about the skew being in a certain direction is the skew is discussed in terms of where the mean is being pulled. And so what happens is the mean is pulled in the direction of the skew, where the further and further data points are. And so the tail in this case is to the right. So the mean is getting pulled further away from the hump in the direction of the right. And just a really quick example, um, there's a story about the University of North Carolina and the major that gives the highest average salary for people that were in that major. And um, it's a little interesting because you would think it might be somebody that's pre-med, maybe going into medicine, or it might be some kind of business major or something where people tend to make a lot of money. But it ended up being history, and that's a little different. And then you realize that Michael Jordan was a history major. Michael Jordan made a lot of money as a basketball player, but he was a history major. And so, what a typical history major makes is somewhere over on this part of a distribution. There might be some people that make a little bit more money than that. And then there's, maybe professors might make in the six figures. And then there's Michael Jordan that makes in the nine figures essentially every year. And this number pulls the mean that way a significant amount. When you find an average and a mean of something, and you have a really, really, really large number that pulls the average to the right very significantly. And so that's why we talk about this as being skewed right, because this data point is going to pull the mean further away from the center, or further away from what we would typically consider to be the middle of the graph. And so the mean in this picture would probably be somewhere around here, even though the hump is further to the left of that. So that's why we call it skewed right. There's no specific definition of unusual values, but we'll talk about some of those right now. So three different types of unusual values. We have outliers, which are way outside the pattern of the rest of the distribution, and we'll talk about a way to calculate those later. Clusters, which are little groups of values that are isolated from everything else. And gaps, which are large spaces between values. So if we look at this data about the fastest times that that are winning races, basically. So times that win races, when we look at that, Usain Bolt and Michael Johnson were way, way, way to the left. There's a giant gap. So the gap is the large space between values. And then if we had maybe 4 or 5 data points over by Bolt and Johnson, we would call that a cluster. Right now, they look like outliers. They're far away from the pattern of the rest of the distribution. But it's important to investigate outliers. And the reason why it's important to investigate outliers is because if we have um, these data points and just pretend like because it's an outlier, then it doesn't exist or we should ignore it, then we're ignoring the fastest time that's ever been run in the 200-meter dash up until um, the time that Usain Bolt had done it. Just kind of ignoring outliers is not good. And this happened with a hole in the ozone layer for a while. NASA had a satellite that was investigating uh, ozone levels, and it was programmed to automatically eliminate any value that dropped below a certain thing, assuming it was just an error on the part of the satellite, an error on the part of the calculation computer inside the satellite. Well, when they went back and looked at these values after they found this hole in the ozone layer, they found that those values were actually accurate. They had just automatically been discounting them, and there was a hole in the ozone layer that may have been that possibly could have been uh, either caused some changes in the way that uh, gases were released, greenhouse gases or whatever. I don't know all the details of the story, but basically the point is you don't want to just eliminate outliers offhand. You want to make sure that you're actually thinking about them and investigating them. Could there be a data error? Yes, but you should always investigate the outlier and not just automatically eliminate it. So looking at symmetrical skewed left and skewed right graphs, these talk about the relationship between mean, median, and mode. In these graphs, notice the mean in a skewed distribution is pulled in the direction of the tail, and the mode is obviously the highest value. The median is close to where we want to actually start thinking about things in a skewed distribution, because that tends to be a little bit less biased. So let's start talking about medians. So we learned how to describe distributions with shape and unusual values. Now we're going to start talking about center and spread. So the median is the middle value, and it divides the data set in half, so there are an equal number of observations above and below the median. And the process for doing that is given. So we're going to have two examples here. Example number one is if we have 7 data points. So what we do is we organize them in order. So 1, 5, 9, 13, 7, no, 14, 17, and 23. And then essentially, since there are an odd number of things, we basically just kind of cancel things off in order until we get to the very middle value. So the median of this data set is 13. If we have an odd number of data points, so in this case 5, 12, 17, 19, 23, and 39, we would cancel things off until we get to the 2 values that are in the middle. And then what we would do is average or take the mean of the 2 values. So in this case, the median of the data set is 18. If it ends up being a decimal, that's okay. So it could end up being something 0.5, and that would be fine. So that's how you find a median of a data set. Now let's talk about resistant measures. So resistant measures are measures that are not affected by outliers or skewness. So if I changed 39 to 399, so let's add a 9. That's going to be a big 9, but let's make it 399. If I have 399, I still cancel things off in the exact same order, and I end up with 18. So median is a resistant measure because this outlier having a skew data set that's going to pull the mean in the direction of the right does not change the fact that the median is still 18. So having some sort of outlier does absolutely nothing in this case. And that's what we have a resistant measure. That's basically what a resistant measure means. So nothing happens. The range of a data set is the difference between the max and the min. So all I do is, since it was already written in order, 25 minus 12 is 13. That is the range of this data set. Note that the range is one number, not 2. Therefore, a lot of people want to say the range is 12 to 25. That's not what we do as range. Range is a number. So we would have to actually do the subtraction. We're not saying 12 to 25. Is range a resistant measure of spread? Well, let's figure it out. Let's change 25 to 250. It's clearly not, because 250 minus 12 is 238. That is a much larger range. And so therefore, it is not a resistant measure of spread. A much more resistant measure of spread is called the interquartile range, or IQR. The interquartile range measures the range of the middle half of the data instead of the entire data set. So this means that we don't really care about outliers because those are on the far edges, either the left or the right, and therefore it's not going to be changing that much if we have some sort of outlier or anything. It's resistant to the effects of outliers and skewness. So we have to identify quartiles in order to do an interquartile range. The first quartile, which we call Q1, is at the 25th percentile. The third quartile is at the 75th percentile. And then the median, which we could also call Q2, is the median. It cuts the data in half. Okay. So to find the quartiles, we split the data in half, and then we split the data in half again. And it doesn't really matter how you do it. In this worksheet, it says if there's an odd number of observations, include the median in both halves. But then, if there are some other things like your TI calculator that won't include the median in both halves, it'll just exclude the median altogether when you're calculating the other ones. So it doesn't really matter. And I'll show you on the TI that you might get a slightly different answer, but it doesn't matter. It's okay either way. So when we look at this test score situation that we had earlier, so 76 is the median. I just simply counted. It's actually the second 76 that is the 15th value. So 66 is going to be Q1. And 1, 2, 3, 4, 5, 6, 7, 8. 88 is going to be Q3. So if we want to find the interquartile range, all we have to do is do Q3 minus Q1. So that's 88 minus 66, which is 22. So 22 is the interquartile range in this problem. The range is much larger. It's 100 minus 12, or 88. So that's how we would do that problem. Again, if I do this on the calculator, it will show up a little bit differently. But what we want to do is compare these distributions. So if we're going to compare, we want to compare shape, center, spread, and unusual values. And you have to actually make comparison statements. So if we're looking at these two periods, basically, and their test scores. And then if we want to write a sentence about unusual values, we would say that period 4 looks like it has an outlier or two somewhere around 25 and 40 compared to the rest of the data.